Hey everybody, and welcome to lesson 2 on magnets. This lesson will cover the magnetic field. What you're going to find is that magnetic fields are very similar to electrostatic fields and carry similarities to gravitational fields as well. Uh, Anybody who's messed with a magnet before knows that it has this incredible ability to apply a force at a distance. If I have like two magnets and I push towards each other, they're either going to pull towards each other or push away from each other. Uh, that means that there's a force that's acting at a distance. It's a non-contact force. And we can say, therefore, that there's a field involved. So let's go ahead and dive into what that field is and how to draw the field lines. Okay, enjoy. All right, everyone. So here we're back with our permanent neodymium magnet, and I have my neodymium magnet, and I have my temporary. Well, right now it's not even temporary. This is just a piece of iron. It's a paper clip. Now it's a temporary magnet, right? Because I can attach my other paper clip to it. So here's what I find particularly bizarre about magnets, and why there's something sort of magical about magnets. If I take my two magnets and I put them north to south and south to north, I feel something between them, right? They're not even touching each other. There is no contact force. And yet I feel a push, I feel a repulsion. If I bring it close to the paper clip, you watch, bring it closer and closer and closer, you notice that paper clip moved before the magnet even made contact with the paper clip. You can also do this, ready, watch. I'm gonna take this one and I'm gonna squish the north side of the top one onto the north side of the bottom one, hold them together and then release, right? They go flying apart. So these magnets, that's a perfect example right there, these magnets are able to experience a force and exert a force on other objects without actually making contact. So we're not talking about a contact force. We're talking about something more similar to gravity or the electrostatic force. Well, this raises the question of how does the magnet apply a force without touching the paperclip? Why is it that I can just have it go flying into the magnet? Right, watch, right off the aim, right off of it. Why is that possible? So let's get into it. And this lesson, we're really going to jump right to the answer. The reason being is I have a lot of confidence that you all already pretty much know the answer, and that's the magnetic field. Right? As we saw with gravity, there was a gravitational field. Electricity, there was an electric field. Magnets are not going to be any different. And the symbol for the magnetic field is a capital B. It is a vector. None of that's going to be too important to us, but I don't want to have you leave this class without seeing it at some point. So the magnetic field, I'm going to define as the field produced due to the presence of a magnet. So when I have a magnet like this neodymium magnet here, just by virtue of the neodymium magnet being here, there is a field all around it. Okay, there's a field that exists all around it due to its presence. When the magnet's not there, that field is no longer present. There is still a field here. There is still a field in this area right here. It's just very small, small enough where it doesn't seem to noticeably affect the paperclip, even though there are tiny, tiny forces on this paperclip due to just the field in my living room right now. But this neodymium magnet has a very large field around it. Okay? When we talk about magnetic fields, we are going to deal with the unit. There are units. The most common units used are the Tesla, capital T, and the Gauss, capital G. Okay? Now, the conversion here is that 1 Tesla is equal to about 10 to the 4 Gauss. And just to give you some perspective, this is a huge number, right? Some of the strongest magnets on Earth are about 10 Tesla. So 1 Tesla is huge. I think it's about the magnetic field generated by a MRI machine, if I remember correctly. It's somewhere in that order of magnitude. So when it comes to a magnetic field, we want to be able to draw one. for us in this class, that's going to be the most important thing to do more than calculating. We're not even going to calculate the magnetic field at all. We're just going to talk about drawing the magnetic field. And when it comes to drawing the magnetic field, we want to talk about a couple of sort of rules. I hate to use that word rules, but we want to look at how we go about drawing them. So number one is when we draw a magnetic field, we're really drawing the direction the needle of a compass would point when it's in that magnetic field. Now, I know a lot of us are not very familiar with using a compass, but what you are familiar with is the electric field due to it. Well, if you remember, the way we found the direction of the electric field was using the positive test charge. This is going to be sort of like using a north test charge. If I could have a monopole, which I can't, right? I can't have that, but we're going to pretend like we do. If I had a north monopole test charge, which way would that north pole move? Well, in addition to that, we're going to look at a couple other rules that are important for drawing these fields. The next one will be field lines never cross. So you'll never have two field lines that cross each other. That was also true with electrostatics, as you may remember. The reason for that is if I have two field lines that cross, well, those field lines basically represent the force, right, on that test charge. Well, then I don't have two individual fields. I have one resultant field. So instead of saying there are two field lines, there's really just one, and that's the resultant. And then in addition to that, we're going to say that the lines, this is related to number one, pretty much the same thing, but start at the North Pole. Well, I just combined those together. And point south. Okay, that's really the same as one. 1 and 3 pretty much mean the same thing, but 3 is giving us a slightly more focused instruction than 1 is. And 4 is that they form complete loops. And that's one way that magnetic field lines are actually different than electric field lines. And I'll show you what I mean by that in just a moment. So here, if we're going to talk about that the field lines point in the direction of the compass needle, we need to kind of talk a bit about how a compass actually works, right? So, let me organize this a bit. So, a compass. All a compass is a little magnet that's set on an axis of rotation. Okay, it's set on that axis of rotation, so when the compass is placed in the presence of a magnetic field, it will experience a torque, which will generate a rotation, causing the compass to point in the direction that we decide we want it to point in, or that's determined by the magnetic field. When I say direction we want it to point in, I mean which side we label north and which side we label south. So looking down at a compass, if this is it, it looks like this, right? It goes like that, and like that. It's like two triangles. That's my axis of rotation there. And what I do is I label one side to be north. Typically speaking, the north is represented as red, so that's the north side of the compass. And then the south side is typically white. Okay, so I have the north side of the compass and I have the south side of the compass. Okay, so here you can see a simulation that I have. There's a magnet here, it's a bar magnet. As usual, the red side, which is the bottom here, is the north side, and the top side, the gray side, is the south side. Up here, I have something that I call a compass, but as we know, it really is just a magnet set on an axis of rotation, an axis that's centered right there in the middle of that compass. Now, or that magnet, I could say. the red side is also north and the white side is south. So when I say that the compass is pointing in a direction, what I'm saying is the direction that this red side is pointing. So right now, the compass is pointing downwards to the bottom of the screen. So if I wanted to, I could go ahead and draw a field line down just like that, right? And the compass was pointing down, so I'll draw the arrow downwards towards the south side of the magnet, which is what we expect, right? As we said, when we draw magnetic field lines, we point towards the south side and away from the north side. Now I can go ahead and delete that. And what I'm going to do is I'm just going to move my magnet up here. And now we see the opposites happening. If I draw the field line, it's the direction the compass is pointing. The red side or the north side of the compass is pointing down. Oh, that's not very good. Okay. The compass is pointing downwards this way. I'll draw my arrow like that. And as we see, again, we're pointing away from the north side of the magnet. As we said, the magnetic field points away from north towards south, or in the direction of the compass. Now, the next thing I can do is take this magnet. I'm going to move it over here. And what we see is our little magnet, or our compass, is pointing up. So the field at this point looks something like this. Okay. Again, that's what we saw in the on the piece of paper that I was drawing. Put all these things together, points away from north, right? Points towards south. We start to see these field lines that look something like this. All right. Now I have another simulation, and what this is going to be is, imagine we take this same magnet right here. Right, we take this magnet, and instead of having it have one compass, we surround it by compasses. What would that look like? Well, it would look something like this. Here, notice, look at every single compass. Here, let me get the little clicky thing going. Okay, this compass is pointing away from north. This one is pointing towards south, exactly like we expect. If we look at a horizontal line that bisects the magnet, you can imagine, given what this one looks like and this one looks like, right? The north one is pointing away from the north, but it's kind of pulling a little bit towards the south. Here, the north one is pulling towards the south, right? Right here, we're going to have a field that looks something like this, pointing up. Same over here. And so if we wanted to draw the magnetic field of this bar magnet, I'm going to click this little thing, line of force, up here, and there we have it. We have these sort of swooping arcs going around, pointing from the north side of the magnet to the south side of the magnet. And then right in the middle here, we have that one that continues off, always pointing towards the south. And here we have one always pointing away from the north. Right? So I think this is a really good visualization of what that magnetic field around the bar magnet looks like. And remember that it points away from the north and towards the south. And we could say the field at a point is the direction the compass's north side would point in a magnetic field. Okay, so back to the lesson. All right, so here, perfect example of magnetism and magnetic fields is the Earth. Okay, the Earth has a magnetic field. Without it, we'd all be pretty much vaporized immediately. If we take a look at the Earth, it looks like this. And we know that it rotates about some axis like this. Well, the purpose of a compass, is to help you find north, right? So if I'm on this part of the Earth, and I have my compass here, when I take that compass, I found this thing. I found this metal, right? Imagine you're in like ancient Greece or something, and you find this little piece of rock that always points in the north direction. So what do? You take some paint, you paint that side that points north, and you call it north. And you know that whenever that arrow is pointing in some direction, it is pointing you in the northward direction. And that works all around the world, right? If I have another one here, and it points like this, I know that this thing is sending me north if I walk in the direction of the piece of rock that I painted. But now this should be giving you a bit of a concern, because this is pointing north, which is absolutely true. This is my geographic north. But we know north doesn't point north. Excuse me, let me rephrase that. We know that north magnets don't point north. North magnets point south, which means that this has to be the magnetic south pole, even though it's geographic north pole. So then the question becomes, what's true? Is this north? Is Greenland north of us, or is Greenland south of us? And the answer to that is yes. Greenland is both north and south of us. It is geographically north, but it is magnetically south of us, which must mean that down here, what we call our geographic south pole must in fact be our magnetic north pole. So north is south, south is north. But what we have to be clear with, are we talking about magnetic or are we talking about geographic? Now that we know that, we can actually model the Earth's magnetic field as sort of like a bar magnet inside the Earth with a north here and a south here. And so I'm going to jump to another simulation in order to show this. Here I have the Earth, as you can see, and a bar magnet in the center of the Earth right here. And I'm using a compass to point. Can I use something else? Right. There's my bar magnet inside the Earth. And fortunately, this diagram shows us the magnetic field lines of the Earth to make things a little bit easier. Now, if we, let me remove this thing, right? If you take a look at the compass in its current position, notice that it is pointing away from north and towards south, right? Go along that magnetic field line, right? My compass continues to point in the direction of the field, right? Follow it all the way along, a complete path to the south. And if you look at the map that we have here, right, we have Africa here and we have Europe here. Obviously, Africa is south of Europe and Europe is north of Africa, but the orientation of the magnet shows south here and north here, further showing that same point that magnetic south is geographic north and magnetic north is geographic south. And this compass is always pointing north, isn't it, right? As I go, well, technically it's pointing in the direction of the field lines, right? But as I go up, it points in the northward direction, or really the southward direction if we're talking about the magnet. Exactly like we'd expect. Another example we can look at, this is a common one that comes up, is suppose we have two halves of a magnet. So I have a north here and I have a south here. When I break it off like this, what I'm saying is you can ignore this half. And as upsetting as this may be, it's as if we're treating it like two monopoles. What would the magnetic field between here look like? Well, it's going to look a lot like a positive and negative charge arrangement. We're going to have something like this. Okay. Just like that right there. All right. Another common type of magnet is what's called the horseshoe magnet. A lot of us have probably played with these before or have seen them in cartoons. This is like that classic bent magnet that looks like this, right? Where we have a north and a south. Really, a horseshoe magnet is just a bar magnet that we bent. So the field is always going to point north to south, so you end up having something like this. With these big arcing fields like this. And then in here we'll have something like this, and you start to have almost a parallel field like that, a uniform magnetic field similar to parallel plate capacitors if these two are perfectly aligned with each other. And then over here you'd actually have some fields that go up and behind the horseshoe magnet like this, but very few. The field back here is going to be very weak compared to the field back here. Now, the rule that applied before to electric fields is still true. If I look at 2 points, let's call them A and B, I can say that the magnetic field, remember that's the symbol for magnetic field, of A is greater than the magnetic field of B because field density. So I'm not going to go into too much depth about that because it's the same thing we did with electrostatics, with electric fields. The denser the field is, the stronger the field is, which is another way of saying the more lines there are, the stronger the field is. Okay, so that is it for magnetic fields. I look forward to seeing you in the lesson recap.